Hi, another method to evaluate the goodness of fit for logistic regression is ROC curve, the receiver operating characteristic curve. So consider the contingency table for actual versus predicted. So that we have 2x2 table, actual and predicted, and the two by two. And we name each number as Tn, Fp, Fn, Tp. So true negative, false positive, and false negative, and true positive. So think about the actual is negative. If predicted is negative, that is true negative, so diagnosed as correctly, diagnosed as negative correctly. If predicted is positive, then that is the false positive, right? And if actual is positive, if predicted is positive, that is true positive. But if predicted as negative, that is false negative. So we define this Tn, Fp, Fn, and Tp. Then we define the two quantities. One is sensitivity and the other is specificity. So sensitivity basically means that how many of actual positive patients are diagnosed as positive. So that is the TP. So basically we are thinking about this group, and the correct decision was made the TP times. So TP over TP plus Fn, that is sensitivity. And specificity is among actually negative group, how many of them are diagnosed correctly. So denominator is this set and the correct one is this. So Tn over Tn plus Fp. And predictor, so the sensitivity and the specificity have the trade-off. So if sensitivity is higher, if the rule, the prediction rule, if we choose a prediction rule that is to make sensitivity higher, then specificity gets lower. Because basically we can decide the threshold between sensitivity and specificity. Okay? So if this is very strict, so this is this side, then we can reduce the number of the positively diagnosed patient. So that means sensitivity gets lower, but specificity gets higher. And if the threshold is very loose, then many people are diagnosed as positive, then sensitivity is higher, but specificity is lower. So we have trade-off between this. And ROC curve, the plot of 1 minus specificity and sensitivity. So this is called the ROC curve. So we can make the threshold for predicted value. So in the previous video, we used the 0.5 as threshold to make contingency table, but we can choose that threshold differently. So 0.1, 0.2, or even 0.99. Then we have different pair of specificity and sensitivity, and if we plot all points, then we can get a curve. So that is called ROC curve. So also that we say all possible thresholds, but actually we only have to think about at most n+1 threshold, because we have only n observations. So we have x1 to xn. So only possible thresholds are here, 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 up to here. So the first possible threshold, second, third, up to n+1. So even if we have multiple predictors, fitted value is a linear combination. So if we order that, then we only have the n possible values. So we only have n+1 possible thresholds. And ROC curve looks like this. So here, actually specificity and sensitivity, but specificity is from 1 to 0. So if we think about 1 minus specificity, then that is 0, 0.2, up to 1. And 1 minus specificity is the percentage, the proportion of diagnosed as positive among actually negative patients. And sensitivity is also the percentage of the positive diagnosed as positive patients out of all actually positive patients. So that both are proportion for positively diagnosed patients. So if rule is random, then specificity, 1 minus specificity and sensitivity are the same, right? So anyway, so if rule is random, so regardless of the patient group, then we have the same probability of diagnosed as positive. So, excuse me. So random rule makes this diagonal line. If some reasonable rule, then ROC curve should be higher than the random rule. So this is ROC curve. And okay, so once we make ROC curve, then you can see that the maybe area under the curve. So this area. So this area may be useful information because random rule, the area is 1/2, but more reasonable rule, even better rule, this area gets larger. So this is called AUC, area under the curve. So AUC is at least 0.5 for reasonable models, and at most 1. So if AUC is 0.9 or 0.95, that is very good rule, good prediction. And if AUC is 0.55, that is probably not very good rule. So that is ROC and AOC. And you can use PROC library to calculate, to make the ROC curve and AUC. And actually the last ROC curve is generated by R and the calculated in this way. So at first we think about the actual number. Actual is either 0 or 1, and it has to be numeric. So so originally the CHD, so heart disease, the occurrence of heart disease is either 1 or 2. So we subtract 1 to make it the 0-1 variable. And fitted value. So this is the fitted probability. So this should be predicted probability. Okay, so if we use these two variables, we can make ROC curve by using ROC function. So the first argument is actual. The second argument is predicted probability. So I think that the second one, as long as it's the some measure, some numeric measure, that should be fine. If not predicted probability, it's fine. So this is why. But if we use the different one, if we use eta in this formulation, that is also fine. But anyway, so this is predictor. So first one actual, second one predictor. Then plot ROC. Then we can get the ROC curve we have seen in this slide. Then if you type ROC, you can see summarized information and you can actually see the AUC here.